Okay, so let's see. Okay, so today we're going to go over Mascal's practice midterm 1, and we're also going to go over the practice midterm that I made as practice. Have you guys tried the practice midterm yet? Yeah, I see. That's good. So the plan here is just to go through this one by one. So are you guys comfortable with converting the nomenclature IUPAC name into the structure, like the bond line structure, right? Where this E and Z 1,2-dichlorobutene will look something like this. Our longest chain is 4 carbons long because of the butte, and we have an alkene at carbon 1. We're at carbons 1 and 2. We also have 2 chlorines like that. Would this be the E or Z isomer, the way I drew it here? Z, that's right, because the 2 highest particles are on the same side, and that means that the E isomer would look like this right here, right? So E and Z isomers are a type of diastereomers, right? And a diastereomer is a type of stereoisomer. So stereoisomers is a big umbrella term for different things. It could be a diastereomer. It could be an enantiomer. Or they could be mesomolecules. Right? So a diastereomer, a type would be E and Z isomers. What does that mean for RNS? Like, let's say we had 2 molecules with multiple chiral centers. What if those 2 molecules are diastereomers of each other? What does that mean for its RNS? Like, does every RNS change, or does some RNS change and some stay the same? Right. Some RNS stay the same. Some change. Which one of these would be all of the chiral centers change, all of the RNSs change? Enantiomers, right? That's all RNS changes. And meso is going to have a plane of symmetry. And 2 chiral centers, which is most oftenly RNS, 2 chiral centers where one is R and one is S, right? But that's not important for what is going to be. It's more diastereomers for the E and Z for chapter 12, right? So since these are diastereomers, what would be the answer for part A? Yeah, stereoisomers, because that is umbrella term for diastereomers. That's not included here. This is not enantiomers because there are no RNS here. Constitutional isomer is a type of regioisomer, right? Where they have the same chemical formula but different connectivity. A rotational isomer would look something like this, where let's say we have that structure, OH, OH. We know that this is a single bond. So if we rotate that single bond, we could get 2, 3, 4, 5, 6, 1, 2, 3, OH, OH. So these are the same exact identical molecules, but I just rotated that single bond to make this backbone a zigzag form, which inverts this dash alcohol into the wedge alcohol, but it's still the exact same molecule. So if you do textbook problems and you like see you expect this to be the product, but the answer key gives this, this is just a rotated version of that, right? So let's move on to the next one. A hydrogen or alkyl shift in a cation rearrangement involves the H or C migrating to the adjacent position with or without the bond electrons, right? Yeah, so it would be with, because let's say we have this carbocation right here, which could do a hydride shift, because adjacent to that, to the left side, that's the more substituted position, where that position has a hydrogen, where that hydrogen with these electrons in that bond right there is going to move right there, right? These two electrons in that bond is going to move with the hydrogen, with the hydride shift, like that, right? Where that bond right there is this bond right here, which moved with the hydrogen. Right? Okay. Now let's look at this one. One propene is that, one butene is this. What is the substitution of this alkene here? Is it mono, di, tri, tetra? Mono substituted. Right. How about the one butene? Mono substituted as well. So since they are equally substituted, they have similar stability. And if they have similar stability, they have similar energy. Right. And what is the relationship between stability and energy? As stability increases, energy decreases, right? They are inversely related to each other. Okay, so now this right here, the C3H5Br, and we have to figure out the number of isomers. The first thing I would do is calculate the DOU, where the equation for DOU is 2C plus 2 minus H minus X plus N all over 2. Right? We have 3 carbons, so that is going to be 2 times 3 plus 2 minus 5 hydrogens. We have 1 bromine, so minus 1 all over 2. 2 times 3 is 6. 6 plus 2 is 8. 8 minus 5 is 3. 3 minus 1 is 2. 2 over 2 is 1. So what can a DOU show you? Like rings or double bonds, that's right. Because a ring represents 1 DOU. A double bond represents 1 DOU. A triple bond represents 2 DOU, which is going to be the next midterm triple bonds. So we know that we either have a double bond or a ring somewhere in the isomers. So let's draw that out here. It was C3H5 8 with a DOU of 1. Okay, so let's try drawing out the 3 carbon chain like that, because we know we have 3 carbons. Let's just attach one of the bromines on here. Can we end here? Can we say that this are molecules? Yeah, we cannot, because if we count the number of hydrogens, we have 1, 2, 3, 4, 5, 6, 7 hydrogens, which is exceeding what we have in the molecular formula here. Right? What can we do to reduce the number of hydrogens in the formula? Double bond, right? Which accounts for the degree of unsaturation. So we could add a double bond here or there, right? So if we add a double bond here, now we have 1, 2, 3, 4, 5 hydrogens, which checks out with the chemical formula, right? Where else could we place the double bond if the is at the same carbon here? Yeah, the second position, which is here, right? Where, what do you guys notice about this double bond here? Mono substituted, tri, tetra, di substituted, right? And what kind of di substituted is this alkane? Trans, right? Where we could draw the cis version of it, which is a different kind of isomer. So that's another possibility as well, right? Okay. What other ways can we draw this chemical formula, do you guys think? Ring, yeah. That's one other way where we can make a 3-membered ring like that. And that could represent our 1 DOU. And we could just attach a bromine anywhere. And we could end there, because that gives us 5 hydrogens. 1, 2, 3, 4, 5 hydrogens. Okay, now there's one, there is one more molecular structure that we could get here. Like, where else could we place the bromine in the 3-carbon chain? In the middle, right? That's right. So if we place the one bromine there in the middle, then we would get that bond there. What kind of di-substituted double bond is this here? There are 3 types: geminal, cis, and trans. What type of di-substituted double bond is this? Geminal, right? Because the two of the groups are on the same carbon. So these are our different possibilities. 1, 2, 3, 4, 5. 5 different possibilities. Yes.
Was there no fast way of doing? You just have to like brute force your way through that.
Yeah, brute force your way through that. Like try different scenarios, but like if you have a bigger molecular formula, then there's gonna be like a lot of them. Like there could be 16, 32, which is why he gave you like a little bit of carbons and hydrogens. So then it's more doable to figure it out and guess and try the piecing all the puzzles together. Another shortcut is to calculate the DOU, which will help you tell you if you have a double bond or ring in your structure. Yes. Yeah, these are constitutional isomers, but 2 of them will be not constitutional isomers. 2 of them will be diastereomers, which are the trans and cis ones here. These are not constitutional isomers because they have the same connectivity, but different stereochemistry because one is cis, one is trans, right? Everything else are constitutional isomers though, right? Any other questions on this part? Okay. Let's go to the next one. So the next one is talking about H2 gas to bubble through a solution of 1,2-dimethyl-cyclopent-1-ene, where our main chain is cyclopent-1-ene with an alkene there. 1, 2, right? So this is our structure here. They said that the reagent is just H2 gas. So let's just put that H2 gas right down here. What reaction does this look like here? We have an alkene with H2 gas. Hydrogenation, right? But what else does this hydrogenation reaction need to go through? A catalyst, right, right. It could be a metal catalyst like palladium or plutonium, any metal catalyst for it to go through. But the question did not give us any metal catalyst, so this would be no reaction. Right. So that was a tricky question because yeah, it's a bit conceptual question. Right. Any questions on that one? Right. So in this case, no reaction. Okay, what if there was a catalyst though? What would be the product? Yeah, the methylcyclopentane, and it's also cis. And why would it be cis? Syn addition, that's right. Because the hydrogens would have to attach on the same side, forcing the other groups to be on the same side as well. That's right. That's right. Okay. Okay. So does anyone know what index of hydrogen deficiency is? Yeah, so that's just another way of saying degree of unsaturation, DOU, right there. Right. Yeah. I know. Yeah, that was my first time seeing that word too. Like when I saw this practice exam, like I didn't know what this was. I had to like look it up. But that's just another way of saying DOU. Yeah. I don't think it was on the textbook as well. That was my first time ever seeing that. Right. Where there are 2 ways of doing this. There's a long way and a short way. So what do you guys think we could do here to figure out the DOU of this structure? Yeah, we could draw it first, which our main chain is cyclopentene. Here, let's say this is carbon 1, 2, 3, 4, 5. And what does methylidine substituent look like?
What's the double bond between the actual like ring?
Yeah, on the actual ring, and the other half of the alkene is the substituent itself. When you see ylidine, think of the alkene. Half of the alkene is part of the main chain. Half of the alkene is the substituent. Right. So we could just calculate the DOU just by looking at this here. Right. Because we have 2 double bonds and 1 ring, how many DOU would that add up to? 3, that's right. The longer way would be counting up all the carbons and hydrogens to get the chemical formula and then use the DOU equation to get the DOU, but that is unnecessary. Okay, so let's draw out 2,3-dimethyl 2-butene. Looks like that. Carbon 2, 2, 3, and 2-butene. Okay. So this question here is asking for the exothermicity of these alkenes. And what does exothermic mean? What is it doing? Is it releasing or gaining energy? Releasing energy, right? And what alkene would release more energy? The more or less stable alkene? Less stable, right? And which one would that be here, given these choices? Yeah, and why would that be the less stable one? Yeah, less substituted. This is di-substituted. This is tetra-substituted. So this is going to be more energy, meaning that it has less energy, so it is less exothermic. Right. Less exothermic than the more unstable one. Right. Okay. So the next question, 3-hexene. 1, 2, 3, 4, 5, 6, carbon 3 alkene undergoes acid catalyzed hydration. What does that mean? What are our reagents if we see acid catalyzed hydration? H2SO4 strong acid and yeah, H2O or ROH. Right. Well, 3-hexene, right? Okay. So what is the first step here? If we have an alkene reacting with a strong acid. Yeah, we protonate one of the carbons, and in this case, does it match carbon we protonate? It doesn't matter because they are equally substituted. That's right. Right. So let's say we protonate one side, the other carbon gains a positive charge right here. And whenever we form a carbocation intermediate, we always have to look out for rearrangement step, like either hydride shift or methyl shift. In this case, we don't have to worry about any because the adjacent carbons are already the same stability as this carbocation here. It can't go anywhere that's more stable. So it is unlikely to undergo rearrangement. Okay. Now we have ethene versus ethane. Okay. So this ethene here, what is the hybridization of this carbon that is double bonded? sp2. How about this carbon here that is single bonded? sp3. Right. Which one of these has higher S character? Yep, the ethene, because it has 33% S character. This has 25% S character. So given that, which one is the more acidic hydrogen? Yeah, the sp2 one right here, because when we try to determine the stronger acid, right, this is what we do first. We first draw out the conjugate bases. Then you rank the stability of the conjugate bases. So if a conjugate base is more stable, would that make it a weaker or stronger conjugate base if it's more stable? Yeah, a weak conjugate base, because if it's more stable, it doesn't want to react. It's less reactive, meaning that it is a weaker conjugate base, which means it came from a stronger or a weaker acid. Stronger acid, right? So more stable conjugate base means it came from a stronger acid. So the conjugate base of ethene looks like this. Conjugate base of ethane looks like this. So the more S character a carbon has, right, the closer it is to the nucleus. which is composed of protons, which are positive charges. And will the negative charge be more stabilized by being closer to the nucleus or destabilized by being closer to the nucleus? More stabilized, right? Because opposite charges attract. We see that this negative charge here is closer to the positive charges, which is why this negative charge is more stable than this negative charge. More stable conjugate base, stronger acid. Right. Yeah. Okay. Let's move on to the next one. Okay. So this next question here, asking about which factors would contribute to calculating or determining the radius the ion travels through in the instrument. So there's this equation that he gave during lecture. I forgot what the equation is. Let me pull it up really quick. Let's see, equation. Where it was radius equals, see what was it? Yeah, radius 2 times mass times the accelerating potential over charge times magnetic field squared over to the power of 1/2. Right. We see that all of these factors are included within the equation. So all of these factors here is involved in determining the radius because all of them are included in the equation. Yes.
Would you recommend for us to like?
Yes, I would recommend memorizing this equation because I remember him testing a math related question on equations he taught about earlier, like for 118A, he asked to calculate the optical activity, which there was an equation for that. Yeah. Yeah. Yeah.
So what each of the values mean?
Yeah. So each of these values here would mean, let's say, the ion mass is the mass of the fragment. Because in mass spectrometry, right, we have a parent molecule and we ionize and cut that molecule into fragments. And do you know what kind of charge the mass spectrometry reads? Negative charge, radical, positive charge, positive charges, right? So the ion mass here is going to be the mass of the cation fragment, right? The exciting potential is the voltage or like the energy of the mass spectrometry instrument, which differs from machine to machine. The ion charge is usually +1 because when it gets cut up into fragments, it usually gives a +1 charge. The magnetic field strength, that can be changed and altered by the scientists. They could like increase the magnetic field strength or decrease the magnetic field strength in the instrument, right? Okay. Yeah.
What is to the right?
To the right.
It's to the power of 1/2.
Oh yeah, to the power of 1/2. Or you can say like this whole thing is square root.
Gotcha, thank
Right. So if we wanted to increase the radius, what factors in the equation would have to decrease to increase the radius? Yeah, the denominator. So the magnetic field strength or the charge, but the charge is usually 1, so we can control the magnetic field strength more likely. Okay. Okay. So now let's go over mass spectrometry alpha cleavage versus beta cleavage. Okay. Let's go over beta cleavage first. Let's say we have this kind of alkene here. When we put this through ionization, we are going to form two fragments, one carbocation and one radical. Which position here do you guys think is going to give us the most stable carbocation? Like this or the other? Right. What would be cation? This or this cation? The one to the left, that's right, because that carbocation that gets formed right there. What can this carbocation do if it is right next to this alkene? Resonance. And resonance makes things more stable. That's right. Yeah. Well, this is a beta cleavage because this is the alpha carbon. This is the right after the beta make a cleavage there. Yeah.
Why it's stable?
Yeah. Resonance makes this more
That fragment itself instead of farther on. Or shorter.
Yeah, instead of like this right here. Yeah, make that cut. Right. We could have, let's say, that fragment, or let's say this fragment here. Right. Though this red are these positive charges here in the mass spectrometry. These positive charges here cannot do any resonance at all because they are not next to an alkene. So that's why these are not the base peak, not the most abundant peak, right? So since this is our base peak here, the question that he could ask you is like, what is the molar mass or the mass to charge ratio of this fragment here? Where to do that, I would draw out all the invisible hydrogens. How many hydrogens are on this carbon here? 2, right? 1 hydrogen here. Now this is the tricky part here. How many hydrogens are on that carbocation carbon originally? 2 as well, right? Because those 2 hydrogens were always there, so we have to keep it there, right? Where we have 3 carbons, where the molar mass of carbon is 12. We have 5 hydrogens, 1, 2, 3, 4, 5. Molar mass of hydrogen is 1. So that is 36 plus 5, which is 41. Right? And that's the AMU, the atomic mass unit of that fragment. Okay. Yeah. So that is beta cleavage. Let's try one more example here. Say. Okay. Let's say we have this alkene. Right. Where would be our most logical fragment? Which one would give us the most stable carbocation? Right. It would be this side or this side. Yeah, the left side, right? Because the first thing we have to do is determine the allylic positions. What allylic mean? Yeah. Yeah, 1 carbon away. And we know that there could be positive charge here or positive charge here. We make, like, let's say, the red fragment cut, we could get this carbocation here. Or let's say we made the pink cut. We could get that carbocation right there with the radical right here. Both of these carbocations can do resonance, right? So since they could both do resonance, the next thing you have to look out for is which one is more substituted. This red carbocation here is more substituted. So that's why this is going to be the major peak, the most abundant peak. This is tertiary allylic carbocation. This is primary allylic carbocation. So this is our base peak right here. The most stable carbocation that gets formed. Yeah.
So if you had one because that had resonance and then another one that was more substituted, which one of those would you consider the more stable?
The one that can do resonance, yes, because a secondary allylic carbocation is going to be more stable than a tertiary carbocation that cannot do resonance. Okay. So that was, now let's go over alpha cleavage. Alpha cleavage is going to involve oxygen or nitrogen where they have lone pairs. So let's look at an example. Let's say we have this oxygen there, right? When we put this through mass spectrometry and ionize it, we can't cleave it right away. It goes through some intermediate first, where which one of these electrons are the most loosely held electrons? The electrons from the bonds or the electrons from the lone pairs on oxygen? Yeah, the oxygen lone pairs are the most loosely held, which is the why it's going to get ripped off first. And what kind of intermediate would that form if one electron gets ripped off? Yeah, positive charge with a radical cation. Right. So this is the intermediate right here, where this oxygen here, it has one radical and a positive charge. This intermediate is called a radical cation. Okay. So now we're gonna do some movement of one electrons. So what kind of arrows do we have to draw if we want to move one electron? Yeah, fish hook, single hook arrow. That's right. Where how many electrons are in that bond right there? 2. So one of its electrons in that bond is going to meet up with the other radical right there, forming a double bond between this oxygen and that carbon right here, right? But we have one more electron here, and that one electron is going to make a radical on that carbon right there. So 3 total arrows, right? 2 electrons were in this bond. One of its electrons is meeting up with that electron to make a double bond. The other electron is going to make a radical on that carbon right there, which that this bond is going to be there. That bond is going to get speed, giving us go and this cation here. Where does this make sense? Like how I cleaved this bond here, I made a double bond there and a radical here. This is called an alpha cleavage because this is the alpha carbon, and we cleave the bond with the alpha carbon. So that's why it's called the alpha cleavage. Where what gets read in the mass spectrometry, this radical or that cation? Cation, that's right. So that's the thing that we calculate for the mass to charge ratio. Right. Let's try another example. This we have this. Right. So the difference between beta cleavage and alpha cleavage is that the cleavage happens after like a certain kind of carbon, like alpha or beta, but also for alpha cleavage, it goes through a radical cation intermediate. We see that in the beta cleavage, it just went for the cleavage right away with no radical cation intermediate, right? So since we have a nitrogen here, we know that we want to do an alpha cleavage, which goes through what kind of intermediate? Radical cation, right? Where we're going to have radical cation on that nitrogen right there. Yeah. Right. Now, what's the next step here? How can we do the alpha cleavage now? Yeah. Right. Like that. That's right. Where we get this radical and this cation there, where this is the base peak right here. Right. So that's alpha cleavage. Yeah.
So whenever we run into an electronegative atom, do we just always like immediately think, oh, radical cation, leave right next to it?
Yeah, with at least one lone pair. At least one lone pair. Yeah. And if you see a double bond, think of beta cleavage. Double bond beta cleavage, electronegative alpha cleavage. Yeah. Okay. So you guys try this next problem here. Okay. Right. So the first thing we do, draw out one butanol. 2, 4. That. The next thing we do, go to the radical cation intermediate. And then from here, we do the alpha cleavage. Where this fragment here is the fragment that has the strongest peak, right? Where it has one oxygen, which is 16 molar mass, one carbon, that's 12, and 3 hydrogens. 16 plus 12 is 28. 28 plus 3 is 31. So it has a mass of 31 AMU here. Any questions on how we got the AMU and the fragment? Yeah. Yeah, from the beginning or from the molar mass? Yeah, so from the mass, oh, you get how we got to this fragment, right? Like the positive right here. So 16 comes from oxygen. That's he'll give you the periodic table, and that's how you can tell like what the molar mass is. 12 comes from one carbon, and then hydrogen is 1. But we have 3 hydrogens, 1, 2, 3. So that's why I wrote 3 right there. If you had like 2 carbons, then you have to do 12 times 2. 3 carbons, 12 times 3. And then you have to get the total mass. Yeah. Okay. Let's do another mass spec problem, which is on the supplement down here, which is part O, letter O. Try this one, and I'll walk around. Yes.
So we're saying if it's alpha plus, are we considering that the first carbon, so if it's alpha? Or like, what are we considering alpha cleavage and whatever?
Okay, so
Alpha plus.
yeah. When we talk about cleavage, that's talking about electronegative atom and oxygen. If you have double bond,
beta.
beta cleavage, right?
So beta is what the.
Beta
This is like relative.
Right, it's gonna be relative to the one that stable carbon, which is that. Right?
Okay, sure.
The alpha carbon is gonna be that first carbon from right there. In the beta carbon.
Okay.
Yeah, we leave the bond after the beta carbon.
Okay, so in reference to whatever carbon that has the stable.
Right. But in reaction, the alpha carbon is considered essentially, but in after chemistry, the alpha carbon.
But wouldn't in this case, wouldn't it be down on them, the tertiary?
Oh, so the tertiary double bond here is not the red.
Okay.
Yeah, we put it like that. A secondary carbon cation that can do resonance, this can be more stable than the tertiary carbon cation.
So when you're saying alpha carbon, like there's alpha beta, it's like alpha is like the first. It's like, say this is the one, and this will be alpha right next to it.
Actually, it's like the when we learn about more reaction, this would be considered alpha carbon, but in mass specs, this is considered. After the
So the carbon on the alpha.
It's the this is the phenomenon. Can you go see the
L one. It's making carbon down here from create resonance. That's what I did.
That's not how it's so when you make that there from side here, the other side. Yeah.
don't know what's going on. And it was,
Oh, yeah, so when we have,
I was preoccupied.
no, so when we have an electronegative atom oxygen right? That's gonna be, if you have double bonds, that's not me, maybe that. Sorry, what's alpha? Alpha, because, this is alpha crisis. But
I know, there might be this, it's just like.
But you have to go through this.
No, it's double so it's
What I thought, instead of that, what is actually.
It is, it's not really giving me. Yeah. Where you-
That makes sense. So then how would you approach this?
Yeah, so for this one, you have to go to most like. If you read the trigger one, that one.
So we just assume.
Okay, wait.
Resonance, is resonance more so, it's like the molecule, like it's that, why, how would you explain that?
Resonance stabilizes because it allows things to move.
Wait, is the charges are like.
What's the front of the wall? Yeah, it's right out of the model, which means it can be
Okay.
Yeah.
When you counted it. For the rain, I'm sick of rain.
I know. Yeah.
I just, I think it's because I just started you.
I know.
That might.
Okay.
What about the other ones? So that means the private. Oh, yeah.
I know. And this is the first time it's like.
But yeah, I mean, that also gives it very.
So, do you guys? Our cyclopentane, we're at carbon 1. We have enol. And when we have enol, then that means that the substituent is an alkene outside of the main chain. Where that propenol is 3 carbons long, starting at carbon 2, there's a double bond right there. So once we have a double bond right here, where is our most stable carbocation going to be at? That carbon right there, right? So if we want the carbocation right here, we want to cleave this bond right here. So let's just do that cleavage and give us our 2 fragments here, right? Now, this is the fragment that we are reading, which has 1, 2, 3 hydrogens, 3 carbons. Wait, no, 5 hydrogens, because this carbon here has 2 other hydrogens. So that's 12 times 3 plus 3 times 1 is 36. Oh, no, it's 5 hydrogens. 5. 36 plus 5 is 41, right? Any questions on this? Yeah, so this is the answer for this part here. Okay. Yeah. Mascal's thing. Okay. Yeah, so the positive charge to be the more stable one. So when we make the fragment, we have to choose the fragment that can do resonance, the one that is the most to give the positive charge. The radical, because the radical cannot be read by the mass spectrometry. It's the positive charge that's read. There will be like flip of those, like the carbocation here, and the radical could have been this as well, right? These are also pole fragments. Okay, now let's alkenes. For history purposes are most involving 2 main reactions. Dehydration. What kind of reactions? Yeah, elimination. E2 is specifically E2 itself. Dehydration is E1 like. minus temperature times the change in entropy. So for a reaction to be favorable, what do we want the delta G to be, positive or negative? Okay. How about enthalpy, delta H? Negative, right? And positive, right? Because if we want to get a negative number, we want to subtract a positive to get a negative number. That's gonna give hydrohalogenated alkene, where in the starting reactant we have two molecules, in the product end up with one molecule. Does that but we are also breaking this double bond right here. And whenever we break double bonds, we G. And that release in energy is very favorable because that gives us a negative delta H. This negative delta H is going to be bigger in magnitude than the delta H. So if it's bigger in magnitude, overall, would delta G be negative or positive? Like negative, right? Because since this is negative, right, the minus sign makes that negative a positive charge because the two negative charges cancel out. But this is a small positive charge. Big negative charge overpowers small positive charge. So it's overall negative. Yes.
Kind of an arbitrary question,
Uh-huh.
but like when you did that mini Ajax reaction right there, I'm not asking for the mechanism that matter.
Oh, like the stereochemistry?
Yeah.
Yeah, so in this case, there is no stereoselectivity. There's no syn or anti-addition because what is the very first step in the mechanism here? Let's say we do this HBr. What's the very first step? Yeah, double bond attacks H, and in this case, it doesn't matter because both of them are equally substituted. Kick out the Br. We get H here. This carbon here lost the bond, so that carbon there gained the positive charge. What is the hybridization of that? sp2, that's right. And sp2, we know they are flat and planar, right? So when this Br minus comes into attack, that flat and planar bond, it could attack on the top side or the bottom side, which is why we don't have syn or anti. If we have something like this instead, though, like let's say alkene with Br2, then there would be stereoselectivity here. Yeah. Right. There would be anti. But we'll go over that when we go over the reactions. Right. So now for this question, reactions involving addition to alkenes generally have favorable. So which ones were favorable in those addition reactions? Yeah, G and H. S was unfavorable because we increased the order. We came from two molecules to one molecule. Right. Okay. Now this IR stuff right here, let's say that was a graph for IR. And you know how IR, there's a fingerprint region where we basically ignore that. At 1600, there's an alkene, 1700 carbonyl, 2100 to 2300, the triple bond region, and then 3000, like the regular sp3ch. And then anything above that is like the alcohol, carboxylic acid, or terminal alcohol right there. The x-axis, think of that as the bond length, right? Because let's say this was the single bond region, we move to the double bond region here, and then triple bond region here. Which bond is the shortest? Single bond, double bond, or triple bond? Triple bond, right? Which is why it is on the lower end of the x-axis because it's the shortest bond. Single bonds are longer, which is why it's towards the right because it has longer length, the longer bond length, right? You can think of that as bond order as well, where bond order and bond length are inversely related because single bond has a bond order of 1, double bond has a bond order of 2, triple bond has a bond order of 3. So the higher the bond order, the lower the bond length. They're inversely related.
If we consider the bond length as the x-axis, why are the C, like sp2 CH hydrogen still on the?
Oh, that I'm not too sure about. Sorry.
Well,
Yeah.
isn't it 3,000? So if it's SPCH, that means they're longer because it has.
No, but then later, I think in the middle of like 2,500, there's still like the nitrogen and also like the terminal alcohol. So I'm kind of confused.
Oh, right, so the alkyne, and the alkyne is like at the 2100
Yeah.
to 2300, right? And then the double bond is like 1600, 1700, and then the single bond is like 1500 below. That's the one that that follows the overall trend. This is like the sp2ch. I'm not too sure why that sp2ch is already over here, right? But
Would the alcohol groups have even shorter bonds for the electronegative elements pull them even closer?
yeah, that's right. Then electronegative atoms pull the bonds even closer, making the bond even shorter. Right. Also, carboxylic acids has a lot of resonance as well, making the bonds even like closer together and stronger and shorter. Axis will represent the intensity, which depends on the sample concentration. Because the more sample concentration you have, the more of a sharp peak we could read. Like the more it could shine infrared light onto and vibrate the bonds. So also vibrational transition probability. Transition probability. Because if we have more sample size, there's a higher probability of vibrating those bonds and seeing a sharper peak on the IR. If there is a lower sample concentration, there's a lower probability of seeing a peak because there's a lower chance of vibrating those bonds. So based on this question, the vertical scale or the y-axis will correlate to vibrational transition probability and sample concentration. If they ask the horizontal scale, it wouldn't be the peak intensity, it would be the absorbance, right? And that depends on bond length and bond order. If they ask for the x-axis, but this question asks for the y-axis of the IR.
The horizontal would be bond length and bond order.
Yeah, the horizontal scale would be bond length and bond order.
That measures the transmittance.
Absorbance.
Absorbance.
Right? Where it is going to be this kind of question right here. Right here. So the units of that would be like inverse of centimeters for the x-axis. Bond order and bond length for the horizontal scale or the x. Back in 19A, like for all we had to worry about was like what peak represents a function more vertical. Like yeah. That's yeah. For vocab. So let's do two diagonal. One, two, three. Currently, it's an alcohol. Two groups like that. Acid catalyzed dehydration will have what kind of reagents on the arrow? Okay, so it's 4 and H2O would be hydration, right? Dehydration with heat. So when you see dehydration, you're starting from an alcohol and you're ending up with an alkene, where your reagents are H2SO4, and heat. If you have hydration, you're starting from an alkene and you're going to an alcohol where your reagents are H2SO4 and H2O or ROH. Yeah. What's the very first step of this mechanism here if we have a strong acid? Yeah, the OH is going to get protonated by the strong acid to become a good leaving group. Right now, it's a bad leaving group. We convert that to a good leaving group by protonating it. Right. Now, think of this as E1-like mechanism now. If we have the good leaving group, that leaving group is just going to leave by itself first, forming a carbocation there on the carbon that lost the bond. Whenever we form a carbocation intermediate, what do we always have to look out for? We have to stop and look out for, yeah, any kind of shifts. In this case, a methyl shift. That's right. Because we see that this secondary carbocation can become more stable at the left side by doing a methyl shift. Right? This carbon here lost a bond, so that is a positive, which is more stable than the previous positive charge because it is a tertiary carbocation. Right? And this blue methyl group here that I shifted is this blue methyl group right here. Now for E1, we have to locate all the beta hydrogens. That's a beta hydrogen, this is a beta hydrogen, and that's another beta hydrogen. We want to look for the beta hydrogen that gives us the most stable double bond, which is going to be the most substituted beta hydrogen. So which one of these beta hydrogens is the most substituted? Yeah, the one on the left side. So we could use the conjugate base that we formed in the beginning as the base to grab that beta hydrogen. This bond between carbon and hydrogen will make a double bond right there. Right. So that would give us our major product here, which is 2,3-dimethyl-2-pentene. Right. Okay. Now the question is asking for 3 minor products. So let's get more space. So that's how we got to the major product. The minor product, one of it would be if we grabbed the less substituted beta hydrogen to make the less substituted double bond. Like that, right? This is the minor product because this double bond here is di-substituted. There's only 2 R groups attached to that double bond. Whereas the major product is tetra substituted. There's 4 groups attached to that double bond. Let's see. Would the other unique minor product be grabbing this or no? Like, let's say we grab this beta hydrogen from a double bond here. Would that be the other unique minor hydrogen, or would it be the exact same thing as this? Yeah, it's the exact same thing because of symmetry. Right. So our other 2 minor products could come from the carbocation that did not do any shifts, the less stable carbocation intermediate. Right. We only have 1 beta hydrogen, which is that beta hydrogen right here. This beta carbon has no hydrogen, so there's no beta hydrogen there. We could use the conjugate base to grab that beta hydrogen and then make that double bond right there. Wait, I'm missing something. Oh, methyl group. Yeah, there we go. To give us that other minor product there. This minor product comes from the less stable carbocation intermediate before the rearrangement step, before the hydrogen step. What kind of alkene is this here? Disubstituted, right? And there's 3 different types: geminal, cis, and trans. This is a trans, right? Meaning that the other minor product is a cis. Like that. right? This is because we know that this is a single bond that could rotate. And then when it rotates, we could get this rotational isomer here. Right? Where now when the beta hydrogen gets deprotonated, we could end up with the cis alkene. So before doing this elimination step here, we could rotate the molecule into this kind of cis-like structure and then form the double bond from that cis-like structure. Yeah.
I just have a view at gem.
Oh, right. Geminal would be cis. So on the exam, if you ask like a vocab question, which one has like higher energy or same stability? The geminal and cis have similar stability, but the trans is going to be more stable than both the cis and geminal. If that's the case, which one will have the lowest energy? Yep, the trans. That's right. Yeah, because it's more stable. Yeah.
J values matter on test.
J values, he did not test J values. He didn't give it on the NMR problem. So, and he briefly went over it in lecture. So I don't think he'll put it on the actual exam. Yeah. But J values are really important to tell like what we have, like if it's a cis alkene, trans alkene. Yeah, like 16, 10. 16 is trans, 10 is cis, and then 7 or 6 is the allylic one. And then 2 is the geminal one. Yeah. But he didn't put that under practice, so I'm not too sure if it's going to be on the exam. Yeah. Okay. So our 3 minor products here, here, and here. This minor alkene product here came from the more stable carbocation intermediate, but the less subside. These 2 minor products here came from the less stable carbocation intermediate before any rearrangement step, like before. Okay. Yeah. What was it? Over here. Okay. So this reaction is an X2 underwater with an alkene reaction. First step here, what would happen with right? But the way that I'm used to it is like one of the carbons here attacks that bromine. Yeah, we form the bromonium ion ring. That's right, that's right. And then at the same time, this other bromine kicks out. But as this bromine here is gaining electrons, is it becoming more or less negative? More negative, right? Because electrons are negative charges. If this alkene is losing electrons, is it becoming more or less negative? Yeah, so this is becoming more nucleophilic. This is becoming more electrophilic. At the same time, that bromine is going to attack the other side of the alkene at the same time, right? And that forms the cyclic bromonium ring.
I believe you like mentioned this before, but like, does onium mean something, like just like the onium suffix?
Onium will mean a positively charged ion. So like oxonium is a OH2 plus, bromonium is a like positive charged bromine ring. Mercurium is a positive charged mercury ion. So it's like onium is like a positive charged thing. If you see 8, that's a negative charge ion, like carboxylate, enolate. But that's later. That's later.
Okay.
Yeah. Right. So I'll write that down. Onium or like neum. Positive charge. 8 negative charge ion. Okay. So let's form that bromonium ion here, where they have to attach on the same side because this attack happened the same time, which forces the bonds to be on the same side. So if this is wedge, that bond would also have to be wedge. What does that make this methyl group here? If these are these that it has to be dash. Yeah, that's right. Okay, we kicked out the Br minus. We have water floating around. So there's a competition between nucleophiles here. This Br or that H2O could attack. H2O, right. This one looks like the stronger one, but it's not because there's a lot more of H2O in the solution, 1,000,000 times more H2O, which overpowers that Br minus. And think of this as opening epoxides in acidic conditions. Yeah, because we have a positive charge solution, so we are in acidic conditions. Yeah,
So is bromine usually a better nucleophile or no? Is it just outcompeting because water is more abundant?
yeah. Well, it's just outcompeting because water is more abundant. If this was the 1-to-1 ratio, then bromine would be the stronger nucleophile. Yeah, because it is fully negative, this is neutral and happy. Yeah,
Is acidic condition ring opening like more substituted?
yeah, more substituted. Like yeah, more substituted. Just like the epoxide opening in 1A. Acidic conditions open in the more subside. Basic conditions open up at the less subside. But all of these reactions here, when we open up the ring, it's always the more subside. We always attack the more subside. Right. So we're gonna use this water to attack the more subside here. That breaks open the ring. Right, where that bond right there breaks off and comes onto that bromine right there, giving that bromine another lone pair of electrons. This will do an SM2-like backside effect, which will invert stereochemistry. So what would be the bond between that oxygen and carbon here if we invert this stereochemistry? Dash, right? Because we're gonna invert that wedge into a dash. So let's draw that out. OH, and this is a dash O. That makes the methyl a wedge. Right. We see that that oxygen is attached to 2 hydrogens still. So what charge would this oxygen with 3 bonds have? Positive, right? Right. This bromine here stays at the wedge because that carbon is untouched. Nothing touches that carbon, so it's unchanged. How can we neutralize this positive charge oxygen? Yeah, we could use water or Br minus as the base to grab that hydrogen and give that oxygen another lone pair of electrons from that bond right there between the oxygen and the hydrogen that is getting ripped off by the water and the Br minus. And that leads to our product here. Okay, so the next one is the weird one. Let's get more space. Okay. So let's say the bromonium ion that is formed was a dash plus wedge methyl, wedge alcohol. You know how previously there was a competition between bromine, water? There's another nucleophile here present, right? Where do you think the other nucleophile could be?
On the hydroxy.
On the alcohol here, hydroxy, right? Where if the nucleophile is on the same molecule as the electrophile, what kind of reaction is that called?
Williams.
Yeah, intramolecular reaction or Williamson. Well, Williamson intersynthesis. This is Williamson intersynthesis like where it is an intramolecular reaction, right? Where in the previous case was intermolecular reaction because the nucleophile was separate than the electrophile. That was intermolecular. If the nucleophile is on the same molecule, intramolecular. And intramolecular reactions always form a ring. So let's say this was the nucleophile here. This nucleophile will attack that more subcarbon, break that up there. I'm gonna for these things to keep track of every atom. Let's say this is 1, 2, 3, 4, 5, 6. Right? When that happens, we're going to get this right here. Right. where this oxygen attacks that carbon and inverts that gas into a wedge right there. This oxygen is still attached to a hydrogen, so that oxygen has a positive charge with 3 bonds. This methyl here inverts from a wedge to a dash. Yeah, no problem. Where this dash bromine is untouched, so that dash bromine stays as dash. Right. So where is this bond going relative to you? Like, what is the wedge bond? Is it going towards you or away from you? Towards you, right? And the dashes bonds are going away from you. So another way to draw this, right, is let's say we could draw it like this, and let's do this as 1, 2, 3, 4, 5, 6. We know that that bond is going up towards you because these are the wedge bonds here going up. That oxygen there still has 1 hydrogen and a positive charge. Carbon 1 has a methyl group going down. Carbon 2 also has a bromine going down. Now, what's the very last step here? How can we neutralize this positive charge oxygen? Yeah, bromine or water will deprotonate and lead to that. This structure here is the exact same structure as that. It's just a different representation. It's easy to see like where the ring is here. Yeah.
Wait, so why isn't the OH outcompeted by water if it's more abundant? Is it just because it's on the same molecule?
Yeah, so they gave us the reactant Br2 and water, right? Where the alcohol and water is going to be like the same equivalence. Like let's say it's a 1-to-1 ratio.
Oh, those are both the products.
The reactants, right? The reactants, these are both the reactants here.
Yeah, but both of those products are those both the major products?
Yeah, these are both major products here. Yeah. Where you know how like let's say we have a 1-to-1 ratio of this alcohol, Br2 and water. When we do the reaction, we only kick out one of the Br minuses. So let's say there's 1 Br minus compared to 1,000 water and 1,000 alcohols. Yeah, these 1,000 overpowers that one thing that got kicked out. So we just ignore that Br minus right there. If there was nothing in the arrow, like no water or no alcohol, then this Br minus would be the one attacking.
Oh, I was asking about the intramolecular, but
Oh yeah. Like
Are
why?
they-
Yeah.
are they both just like happen? Are they both just being formed?
The same time. Right.
So it's like every time you have some sort of like leading group and then like nucleophile, so it's like in this case it's OH, then you'll have like the intramolecular reaction.
Right.
It's like also like let's say if you were to have like, I guess like a linear alkane or alkene.
Yeah.
And then you have like OH on one side
Mm-hmm.
and then
Yeah. Right. That right here is going to do the same thing as well.
Yeah.
Like Br2, and it could be under water or alcohol or by itself, but this would be one nucleophile that attacks the more subside of the bromine against water. Yeah, that's right. I think there's an example of that I have on the practice I made here, which is like this mechanism here. Like I give you an alkene with an alcohol. Yeah.
So you think if it was like to predict the products and then it just showed the starting material, you should just draw them. They're both like possible, they're both like half.
Yeah, I would draw both, right? Yeah. See, mechanism, that's done. Okay, now, these predicted products are like, yeah, question?
Wait, so come up, Albert was saying that, what's it called, okay, the predicted products, is there a major winner? Would there be a difference in that? One's intermolecular and the other one's.
Oh, right. I would say that this is the major one right here, because intramolecular reactions happen faster than intermolecular reactions. the top two fastest reactions in OChem are intramolecular reactions and acid-base reactions. They happen way faster than intermolecular reactions, right? But since he included both products, he wanted you to draw the mechanism for both products. But this one here should be the major product. Yeah, the intramolecular one. How do you guys feel about the reactions, like predicted products for here? Like once you have the reagents, recognize what reaction it does, and then like recognize if it's Markovnikov versus anti-Markovnikov, syn addition versus anti-addition, right? So if you see BH3, H2O2 here, what kind of reaction do you think? Hydroboration oxidation, right? And hydroboration oxidation, let's think about the regioselectivity. Is it Markovnikov or anti-Markovnikov? Anti-Mark. How about the stereoselectivity? Syn addition or anti-addition? Syn addition, great. So the alcohol and H has to be on the same side. So let's say we put an alcohol as a wedge, the H also has to be a wedge. That forces this methyl to become a dash. It could have also been dash OH and dash H, which forces the methyl to become a wedge like that. Yeah, plus an enantiomer in this case. If there was a pre-existing
You'd have like a wedge on another of the guys.
yeah. And you didn't have to draw out these hydrogens, you can just let them out as invisible as well. Those hydrogens right there. The reason why I drew that out is because I'm showing the syn addition. They're adding on the same side. Yeah.
Do you think that the test we would be for us to draw the hydroboration
Mechanism?
Yeah.
I don't think so. I don't think so. But I don't know. This is Mascal's first time teaching B, so I can't predict. So I can't predict it. Yeah. Yeah.
Both, or can you just do like plus one?
Yeah. You can do plus minus in this case.
Or can we also just draw one of them and just say it's racemic?
Yeah. Yeah. You could also say racemic mixture as well. Racemic mix, or you could say plus enantiomer. If you have this, then you can't do it. You can't do any of these. Because then these would be diastereomers. Yeah.
I know I'm playing backtracking, but like if I just drew one though, it would be fine.
Draw one and then.
Yeah, one enantiomer thing.
Yeah.
It depends on how he grades it and how the TA grades it. Because I know for Nasiri and Helix, they want the plus enantiomer as well, the plus minus. But on his key, he only put one of it. Yeah. I would just put both just to be safe. And he can take points off of that because that's not wrong. If he does take points off, then I would just like request regrade and explain like they are enantiomers or like they can attack on either side. Yeah. Okay. Ozone analysis. There's a trick to this reaction. So let's say we have a simple alkene like that, and the reagents are O3 and some kind of reducing agent like H2S, Me2S, or NaHSO3. Right. The most important thing here is O3. If you see O3, think of scissors, right? Which is going to snip this alkene in half and then put oxygens in the middle like that. When we snip it in half and put oxygens in the middle, these are our two products there, and that's it. Yeah. Right. Yeah. Where it could get more complicated because if it's in a ring like this, and then we do the same thing, we snip it in half, we won't get two products. In the previous example, we got two products because this was in a linear chain. When we cut that linear chain in half, we get two separate molecules. But if we cut open a ring, we still get one molecule. We just opened up the ring into one linear chain. Yeah.
A question about osmosis.
Yeah.
Let's say you had on that cyclopentane, let's say instead you had like an ethylene on the top, would that give you an anhydride and then the pentane with the ketone?
Anhydride. Oh, anhydride is something else. Oh, formaldehyde?
Sure.
Yeah, it would be that. That's right. Right. where we could also snip this alkene in half, put oxygens there, and we get these here. What? Oh, and be careful because these bonds are still attached to each other. We did not cut those bonds at all, right? Because some people they make these bonds separate, but we did not cut those bonds. The only bonds we cut are the double bonds in half. We did not cut that bond in half. Okay. So if you view your answer as this is correct. But if you want to make it more aesthetic and you have like more time, you could number it like 1, 2, 3, 4, 5. Redraw that. 2, 3, 4, 5. At carbon 1, there's an aldehyde. At carbon 3, there's a ketone. At carbon 5, there's an aldehyde. And this right here is the formaldehyde. There. But you don't have to redraw it. You can leave it as this, which is the exact same thing as that. Okay. So this right here, he's asking you to predict like what these products came from. We have 2 of these, and something reacted with ozonolysis to give 2 of these, right? So what do you think could have been cut up to get 2 of these? This, right? Because we know when we cut it in half, we get these 2 products here, which is 2 of that. Yeah. Okay. Okay, let's try this thing here. Try D, part D, question D.
You don't need to know aminolysis in extreme conditions, like acidic conditions where a terminal aldehyde will become, or an aldehyde will become a carboxylic acid, right?
Yeah, I think you can get about the KMNO4, right, yeah, that is also one reaction, but Mascal didn't cover that in that share.
So we don't.
Yeah, so we don't need to worry about that. Well,
He told us to read the book.
yeah, he said read the book, and then if he puts on the test, and then you try to complain it, and then he's like, oh, I said that in the beginning of class, read the book. Yeah, I'm not sure. Yeah.
Which page was it?
The KMNO4 reaction. So it doesn't exact same thing as post analysis,
Okay.
but whenever you have an aldehyde, that aldehyde goes all the way to carboxylic acid. So think of it as like PCC and Jones. You know PCC starts with aldehyde.
Yeah.
For primary alcohol, Jones goes all the way to the carboxylic
So-
acid.
It just oxidizes the product.
Yeah, oxidizes the product all the way to carboxylic acid.
You know the reason behind that?
I'm not too sure the reason behind that. Yeah. Yeah. Where let's cut all these double bonds in half, put oxygens in the middle. Wait, final product.
Wasn't also just not happening. So this happened.
Yeah, happens on all of them. There is one reaction that reacts with only the most subcarbon though.
Yeah.
And that is MCPBA peroxy acid one.
Mhm.
Right? Because let's say you have something like this reacting with one equivalent of MCPBA. Which alkene would it react with?
The top
Yeah, the top one. And what does MCPBA does to the
mixed.
epoxide? That's right.
And the rest of the reactions that can like form like things to multiple double bonds, it just does its all.
Yeah. Like the
Like hydrogenation just about.
Yeah, hydrogenation does it to all of them as well. And also dihydroxylation, the aluminum tetroxide, OSO4.
It just wouldn't happen to benzene, right, because the resonance.
Yeah. Yeah, we don't want to touch the benzene unless we have high heat, 300 degrees Celsius.
Mixed epoxide with the most substitute.
Yeah, the MCBBA mixed epoxide with the most substituted, if we only have one equivalence. If you have excess, then it does it with all the alkenes. But first, the most substituted one first, and then the second equivalence reacts with the second most reactive, like second most stable. Okay. Now. Okay, we have a good leaving group. And what kind of reagent is this called here? What type of reagent is this? Is it an oxidizing agent, reducing agent, base, nucleophile? Strong nucleophile and strong base, right? So a tip to know about that, right, is if you have a negative charge on an oxygen or a negative charge on a nitrogen, these are strong bases. Right? And if you think of strong base, think of elimination reactions, like E2 reactions. And there are two types of bases you could have: unhindered bases and hindered bases. There's only two types of hindered bases that you need to know. The LDA is one of them. Yep, and turbotoxide, or that chicken leg base, right? And it others everything else like ethoxide, NaOH, NH2 minus, anything else. So we have an unhindered base. So if we have an unhindered base, do we want to go for the Zaitsev or Hoffman E2? Zaitsev, we want to make the more stable double bond. Hindered base goes for the Hoffman. Okay, so, and what is the transition state name of the E2 reaction? For SN2, it was backside attack, anti-periplanar, right? And what does that mean? What does anti-periplanar mean? Like, what has to be anti to each other? Yeah, the beta hydrogen and the leaving group. The beta hydrogen has to be anti to the leaving group. So usually we're used to seeing like the leaving group as a wedge or dash, where we have to take the hydrogen that is anti to that. So if the leaving group was a wedge, we want to look for the beta hydrogen that is a dash, and vice versa. In this case, we don't have a wedge or dash. We have a flat bond. We can still do anti-periplanar here by making this bond the reference bond right here. We see that the leaving group is on top of that reference bond, and the beta hydrogen is on the bottom. So they are on opposite sides. One is up, one is down. So that's still anti. So we can still do E2 here by grabbing that beta hydrogen. This bond between that carbon and hydrogen will make a double bond there, and we will kick out the leaving group here. Right? All these three arrows happen at the same time, simultaneously for E2. The first one was the strong base deprotonating the anti-beta hydrogen. The second arrow comes from the carbon and hydrogen, making a double bond there. And then the third arrow kicks out the leaving group. Okay. And that would form a double bond like this. And the stereochemistry does matter here, where let's look at this carbon here. Is R1 cis or trans to R3? Trans, right? So we want R1 to be trans to R3, like that. We see that R2 is trans to R4. So we want R2 to be trans to R4. Another way you can think about it is that you see R1 and R4 are cis to each other. They're on the same side. R1 and R4 are also cis to each other. You could have also flipped this as well. Like you could put R1 up here, R2 down here, but that means that you'll also have to flip that as well. If you only fit one of them, then that would be wrong because they have the wrong stereochemistry. Right? Yeah, no problem. Okay. So we see in the product, we formed an alkene from an alcohol. What reaction would form an alkene from an alcohol? Yeah, dehydration. So this is just H2SO4 and heat. So alcohol to alkene, dehydration. good leaving group to an alkene, E2. The reagent for dehydration, strong acid and heat. The reagent for E2, strong base. So they're opposite from each other. So let's say strong base. And that strong base could be hindered or unhindered. Right. Okay. That's it for reactions. Oh no. Okay. So we have an alkene here and a good leaving group. So what reaction was made here? Yeah, E2 Hoffman. So we could use a hindered base like turbotoxide or LDA for the Hoffman product. Right. Yeah.
LDA, what solvent do you want to use?
LDA, the solvent, you could use any like neutral amine solvent because LDA has a nitrogen negative charge with lithium on it, where the solvent is usually like the same atom as the nucleophile. So you could use the product version of it, like with the NH, like that. Right. But you don't need to put the solvent in the synthesis column. You can just put LDA and then it will be accepted. Right.
But then for turbotoxide, don't you need to put like CH3, okay?
Yeah, that is the solvent as well. But for synthesis, they will accept this as the answer. Yeah.
You could not use it, you just.
Oh,
You could also see as TBU OK or NA, or you can see it as CH3 COK or NA. The K or Na part means that it is fully positive charge, making that oxygen fully negative, like that. But that's the exact same thing as this here. Okay. Osmium tetroxide. What does this reaction do to the alkene?
It's the dihydration.
Yeah, the dihydroxylation. Right, we add two alcohols on both sides of the carbon. And what is the stereoselectivity? Syn addition or anti-addition? Syn addition, right? That's the important part, where both alcohols have to be on the same side of each other. Yeah.
I was looking through your notes and what was the name of the one where it does anti? Like the, yeah, it has like a phenol thing. It was like PCO. Yeah.
Oh, this practice one right here.
Oh,
Yeah.
No, it was like PHCO3, like something else. Like the whole point of it is that it's still the dihydroxylation. It's just that in context with a different solvent,
Yeah, it's not in here.
it
it's in
did.
the-
I see. So you know how this is a syn or cis vicinal diol? So this is cis because they're on the same side. Vicinal meaning that they are adjacent to each other. Diol meaning that there's two alcohols right there. Let's say we wanted to synthesize a trans vicinal diol, where the alcohols are trans to each other. We cannot use osmium tetroxide reaction anymore. What we could do, like let's say we start with a double bond right here. What is one reaction you know that can add a good leaving group like bromine and alcohol on the other carbon? Right. Like let's say we wanted this right here.
Is it the homogenation and then put like water on it?
Yeah, halogenation, Br2, H2O. That's right. Which will add bromine on one carbon, alcohol on the other carbon. And this reaction here is anti-addition. Okay. Back in monosine A, what are the two ways to make epoxides?
MCPBA.
Yeah, MCPBA, which comes from an alkene, But what if we have a bromine right next to an alcohol? Intramolecular Williamson ether synthesis. And do you remember the reagent that's needed? How can we make this oxygen negatively charged? We want to use a strong base, like NaH. Where you know how the H is the one with the negative charge? That H minus is going to deprotonate the alcohol and give that alcohol, oxygen, a negative charge right there. Now, this is our strong nucleophile. Is this an electrophile or a nucleophile? That carbon right there. Electrophile, right? Because it is, well, what is the partial charge of this carbon here that's attached to the really electronegative bromine? Partial positive. So this nucleophile here attacks that electrophile and kicks out that leaving group. So that is an SN2 reaction, but it is an intramolecular SN2 reaction. And why is it intramolecular? Same molecule, right? The nucleophile is on the same molecule as the electrophile. And what do we always form in all the intramolecular reactions? A ring, right? Where that ring is going to be this ring right here, where it inverted this dash into a wedge like that. So this is our epoxide right there from Williamson ether synthesis, intramolecular Williamson synthesis, right? Now, there is one way for us to go from this epoxide to this trans diol here. What reagent can we use to make it trans and add another alcohol? So what is the nucleophile that we want to use to add another OH there? Yeah, you could use strong acid or strong base. It doesn't matter. Like if you're this, yeah,
Sodium hydroxide or sodium.
yeah, sodium hydroxide or H3O plus. Right. Let's say we were in basic conditions, right? Let me make more space here. Right. This is the epoxide right here. Let's look at basic conditions first, like NaOH. The OH has a minus charge, which is going to attack that electrophilic carbon and pop that epoxide over there. When that happens, that wedge gets converted to a dash, OH. And this oxygen here is that oxygen right there with its wedge bond still. Which is why in basic conditions, what kind of step do we need at the very end to fix that charge? Acid workup, that's right. Like H3O plus or H plus. It's just gonna protonate that O minus to become OH. And that's our trans-vicinal diol right there. Right, that was basic conditions. We could have also used acidic conditions, which would give us the same product, but different mechanism. Where let's say we used H3O plus. Since this is a strong acid, that oxygen is going to get protonated and become a positive charge epoxide now. Right. And then we kick that water, which that water is going to attack that carbon, kick that epoxide up there. And that's going to give us OH here. And that inverts the wedge to a dash, giving us that. And what's the last step here? How can we get to this from here? Yeah, base like water in acidic conditions, right? Which is going to deprotonate that and give that oxygen another lone pair, giving us our trans-vicinal diol that we want here. Right. So to summarize everything, here's a quick flow chart on, let's say we have a double bond here, and let's say you wanted a cis vicinal diol in synthesis versus if you wanted a trans vicinal diol. The first reaction we went over was osmium tetroxide, which is the new reaction that you guys learned about. That leads to the cis vicinal diol. If you want the trans vicinal diol, then you would first use MCPBA to make the epoxide. And then the second step is going to be NaOH or H3O plus to get the trans vicinal diol. So it depends on what you want for synthesis. These are your different routes. So next that. Okay, what do you guys? Okay, let's do the synthesis here. Let's say we have Br, and we want to convert that into BrOH. What is one reaction that we said makes a bromine and alcohol vicinal to each other, adjacent to each other? Yeah, Br2H2O. So let's work backwards. Where this could come from, Br2H2O, where our double bond has to come between these two carbons right here, like that. How could we create a double bond from a good leaving group? What is that reaction? E2, right? Where we could use any strong base, and it doesn't matter if it's unhindered or hindered because both carbons are equally substituted. So we could use ethoxide or NaOH for E2. And then the second step was halogenation in water. Two-step synthesis. Yeah.
The stereochemistry coming from.
Yeah, there would be stereochemistry, but since he didn't include it in the synthesis column, then you didn't have to worry about stereochemistry. What's the accurate stereochemistry here? What's the relationship between these two bonds? Anti, right? That's the accurate stereochemistry. Yeah. Yeah, so yeah. Okay, more. Okay. Yeah, this one is a weird one. Like, the first thing you do, calculate DOU. So that's 2C plus 2 minus H minus X plus N all over 2. 2 times 4 plus 2 minus 6 minus 2 all over 2. 2 times 4 is 8. 8 plus 2 is 10. 10 minus 6 is 4. 4 minus 2 is 2. 2 over 2 is 1. So we have 1 DOU, right? And what is this region here? 1500 and below. Fingerprint, right? So we could ignore that one. And what is the 3000 peak here? Yep, sp3ch, which is like usually always there. If we see anything to the left of it, like 3100 sharp peak, what does that peak tell you? Yep, sp2ch, which looks like this. That H right there is bonded to an alkene carbon, right? But this is weird because where should this peak show up as on IR? 1600. Yeah.
Actually, ask Mascal about this.
Uh-huh.
It was confusing. It was like, at least for us, like you don't need like both of them.
Oh, really?
It was like the 3100 peak. He said it's like enough information, I guess, to show that it's sp2ch.
Oh, well, dang, that conflicts with Leibniz because
Yeah.
she says that
Yeah.
whenever you have this paper here, you will always pair up with that.
Yeah, that's what I told him.
Did that
It was
for
like,
18A as well.
Yeah, yeah.
And what he said,
Did he say you don't need it or?
yeah, he just said it's like, he just said it's enough. So I was like, oh,
No.
okay.
That's inaccurate because we do have that peak there, which should show up there.
Yeah.
Yeah. So. Yeah. Right. Yeah. We have a double bond. where let's put that double bond right there. And he doesn't give the integration as well, like how many hydrogens are in each peak. So we have to like guess what it is. But
I remember he was like, oh, I'll
The-
put it there if it's necessary.
if it's necessary,
I think he said that in
uh,
class like yesterday.
then so he might put J values that if like he changes things up in the practice exam. But to guess it, look at the height of the integration, right? The height will represent the number of hydrogens. This is the furthest, so it has the lowest amount of hydrogens.
Probably like,
Yeah, probably 1. Making this probably 3. This is probably 2. To confirm that, add it all up to 6. We have 6 hydrogens on the formula. So this is our integration here. What is this region here on the HNMR between 5 to 6? Alkene hydrogen, right? So let's label this A, B, and C. And let's say that this hydrogen here on alkene is hydrogen A. How many neighbors does hydrogen A have if it is a triplet? 2 neighbors, that's right. So we could say it's 2 neighbors or these 2 neighbors right here. Right, so if these are the 2 hydrogens on the structure, because we need 2 neighbors for that hydrogen A, which peak has an integration of 2? B, right? And what do you notice about where it is located at? Next to an electronegative atom, because it is D-shielded, it's around the 3 to 4 range. What's our most electronegative atom on the formula? Chlorine. So it has to be next to chlorine. Because we know that it is really D-shielded, 3 to 4, next to an electronegative atom, which is chlorine, like that. How many neighbors do these 2 hydrogens have if it's a doublet? 1 neighbor, right? Which is 1 neighbor is that hydrogen A right there. So these we could say is hydrogen B right there. Now let's look at this right here. What do you guys think this could have came from? 3 hydrogens with no neighbors. Yeah, and our methyl group coming out like that. Right. And those 3 hydrogens are these 3 hydrogens right here. So these are the C hydrogens, C, 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 with 0 neighbors. So let's count what atoms we used. We used up 1, 2, 3, 4 carbons, so we can't add any more carbons. We used up 1, 2, 3, 4, 5, 6 hydrogens. We can't use up any more hydrogens. We used up 1 chlorine. We are missing 1 more chlorine, where we could put that 1 more chlorine right there. Right. We can't put the chlorine right here because that would make that integration too. The only spot we could put is right here, because that can't be a hydrogen. If that's a hydrogen, then we would have another peak in the alkene range here. We only have 1 alkene hydrogen, which is that 1 peak right there. And 1 DOU is accounted for by this double bond right there. The most important, the most confusing thing is this thing here. Like that's supposed to be there. Yeah.
Is there supposed to be a peak there
At 1600.
for the alkene?
Yeah, it's still supposed to be there, right? But I think Mascal like says you don't need it. You just need the 3100 peak. But if you have the 3100 peak, that always pairs up with the C double bond C, which is this peak right here. Yeah.
yeah, that was a big.
Yeah. Yeah, like this sharp peak right here is like you can make a line through the 3000 peak like that. If you see a peak to the left of it, then that's a sharp peak right there. Okay. Okay, and then this is just extra practice problems. Have you guys tried any problems yet, or have any questions on this? Okay, let's see. Which ones do you guys want to work on for here? The vocab, the reactions, nomenclature, or synthesis? Or mechanism? Let's do synthesis. Okay. Let's do this one here. We're going to convert this molecule into this molecule here, right? So the first thing I do for synthesis is I determine what's the similarity between the reactant molecule and the product molecule. Right, where the similarity is this backbone chain right here. Then I determine what's the difference is. The difference is this bromine and that nitrile right there. Back in 19A, what is one reaction that you know could add a nitrile on, let's say, an electrophile? Yeah, SN2, right? Where how can we make this carbon electrophilic? How can we give that carbon a partial positive charge? Yeah, halogen, like bromine, right? And we could do NaCN, where that Cn minus can attack that carbon and kick out that bromine to give us the Cn here, right? Now, what do you guys think is gonna happen in the first reaction here? Yeah, no problem. So if we do Hoffman, we would get a double bond right here, right? Which is far away from where we want the bromine to be. We want a double bond right here. How can we create a double bond right there? Unhindered base, right? Like NaOH and water. Which we do in E2 Zaitsev, like this right here, right? Okay, let's go backwards. You notice how this bromine here is on the less subcarbon? Like, let's imagine there's a double bond there. What is one reaction you guys know that adds a bromine to the less subcarbon and a hydrogen to the more subcarbon? Yeah, which is HBr and ROR, peroxide, which came from that double bond right there. Okay. Now, how can we convert this double bond to this double bond here? Yeah, let's do the same thing here. Let's do HBr and ROR again. Where would that put the Br on this alkene here? Yeah, the secondary carbon. So let's say we put a bromine right there. How can we make this less substituted double bond from this good leaving group? Yeah, Hoffman turbotoxide. So the first step was E2 Zaitsev. Second step was anti-mark HBr. And then the third step was E2 Hoffman. And then this was, the fourth step was anti-mark HBr again. And then the last step, SN2 reaction to substitute the bromine with the nitrile. So we just crawled all the way to the end of the chain by doing a lot of anti-Markovnikov and Hoffman stuff. Because you know how anti-Markovnikov and Hoffman stuff creates the less substituted and the less substituted side? We see that the new group is on the less substituted side, so we want to crawl all the way there by doing a lot of anti-Mark and Hoffman reactions. Okay, let's try this one here. What do you guys think happened in the ring? Yeah, what was that? Yeah. Oh yeah, it opens up, yeah. And what is one reaction that cuts up a ring? Oh, so that will not open up the ring, but it will add a halogen on there, right? Yeah, ozonolysis, where we want to cut up the double bond in the ring, but how can we make a double bond here? Yeah, E2, like NaOH and water. So let's say that became double bond there. And then let's do ozonolysis. O3. H2O. Yeah, so PCC is an oxidizing agent, right? Where you know how these are the products here? We have aldehydes. If we convert aldehydes to alcohols, is that oxidation or reduction? So, yeah. Right, like let's redraw this as 1, 2, 3, 4, 5. This is going to be 2, 3, 4, 5. This is 1, 2, 3, 4, 5. Well, at carbon 1, we have an aldehyde. Carbon 5, we have also an aldehyde. 1, 2, 3, 4, 5. Okay. In 118A, how do we convert an aldehyde to an alcohol? Yeah, reducing agent. Reducing agent, like lithium, aluminum hydride, LiAlH4. Second step, acid workup. Going from primary alcohol to aldehyde is PCC. That's oxidation. But if we want to go from aldehyde to primary alcohol, that's reduction, usually reducing agent.
Isn't, NABH4 relevant?
Yeah, you could also use NaBH4 as well instead of LiLH4.
Okay.
Yeah. BH4 to H plus. But if this was a carboxylic acid, you can't use NaBH4. You had to use LiLH4 if that was a carboxylic acid. Right. Yeah. And let's say instead of alcohols, we had carboxylic acids. What would you have to do to convert an aldehyde to carboxylic acid? Yeah. Jones, strong oxidizing agent. Because we want to oxidize the aldehyde to the carboxylic acid, which we could do Jones to oxidize that there. So it depends on what your product molecule is, and then that like has different reagents and reactions that you need to do. The first reaction was bromination. Second reaction was E2. Third reaction was ozonolysis. And then the last step was reduction. Yeah, and that is it. Any questions?